All right, Math 30-2. Today we're going to finish the notes on permutations with regards to factorial notation. All right, look at this example. An internet site's access code consists of 3 digits. Knowing the 3 digits is not enough to access the site. The digits have to be entered in the correct order. The order of the arrangement of the digits is important. John cannot remember the access code except that it contains the digits 3, 5, and 7. List all the possible arrangements of the 3 digits that John could use to determine the access code. Well, we could have 357, or we could have 375. We could have 537, or we could have 573, and finally we could have 735 or 753. So those are all the possible arrangements. There are 6 of them, and only one of them will access the site. This type of arrangement where order is important is called a permutation. So permutation is an arrangement of objects of a set of elements in which the order of the elements is important. Can't stress that enough. That's a permutation. Order is important. Permutations with n different elements taken n at a time. So let's list all the arrangements with the letters of the word cat. Well, you got CAT and CTA. You got ACT and ATC. And you've got TAC and TCA. Write the number of permutations in factorial notation. Well, that gives us 6, and we know that in factorial notation that would be 3 times 2 times 1, or 3 factorial. This is an example of the following general rule then. The number of permutations of n different elements taking all at a time is n factorial. We've got 3 different elements, CAT, taken all the time is 3 factorial. There are 6 possible arrangements for the letters in the word cat, taken all 3 at a time. Determine the number of permutations of the letters of the word Regina. Well, there's 6 letters in the word Regina. If we're going to use all of them, that would be 6 factorial. On your calculators, that would be 7. Clona has 7 letters, so that'd be 7 factorial. Solution to 7 factorial with your calculators is 5,040. Permutations with n different elements taken r at a time. Note that r must always be less than n. Important statement. All right, so let's use the fundamental counting principle to determine how many 3-letter arrangements can be made from the letters of the word graphite. So now in graphite, there are 8 letters. So if I just used all of them, that'd be 8 factorial. However, we don't want to use all of them, so we don't want to use the factorial idea. We just want 3-letter arrangements. 1, 2, 3-letter arrangements. So there's 8 letters. That means 8 can go in the first spot, any one of those 8. I've now used 1. There's only 7 left. I've now used 2. There's only 6 left. So 8 times 7 times 6. That's the number of 3-letter arrangements or 3-letter permutations. 8 times 7 times 6 is 336. In the example above, we found that the number of permutations of 8 elements taken 3 at a time is denoted by the notation 8 permutations of 3. 8 permutations of 3 is equal to 8 times 7 times 6. Or we could say, in factorial notation, that would be 8 times 7 times 6 times 5 factorial divided by 5 factorial. Or if we write it as this, 8 factorial over 8 minus 3 factorial, where 8 is our n value and 3 is our r value. This is an example of the following general rule then. And this formula is on your formula sheet. N permutations of r will equal n factorial over n minus r factorial. If we take n different elements, r at a time, and remember r must always be less than or equal to n. And we said that earlier, right? R must be less than or equal to n. So we can never take a certain amount of objects and organize more than we've got. That wouldn't make sense. So use the NPR key on a calculator and evaluate 8 permutations of 3. Again, we have to type in the N key first, the N value. So if we're doing 8 permutations of 3, we're going to type 8 on our calculator. Then we're going to hit our math button. We're going to go over to probability. And we're going to go down to the number 3. Sorry, not 3, number 2 until you see the NPR key. Hit that. And then you're going to type in the number 3, your R value. And that would be 8 permutations of 3. And that should give the same values we had before, 336. All right. Defining 0 factorial. We talked about this yesterday. Let's have a quick look at it then. If we replace R by N in the previous formula, we get the number of permutations of N elements taken N at a time. We know this is N factorial. If you take 8 elements all the time and arrange them, we just proved that that was 8 factorial. So if you plug that into our formula, where R becomes N, we get this idea, N factorial over N minus N factorial. Well, N minus N is 0. We keep the factorial sign. We know that this is true. In order for that to be true, 0 factorial must equal 1. So 0 factorial is defined as having a value of 1. Example 6. In a region, vehicle license plates consist of 2 different letters followed by 4 different digits. If the letters I, O, Y, and Z are not used, determine how many different license plates are possible by using. So we've got 6 spots on our license plate, 2 different letters followed by 4 different digits. We can't use the letters I, O, Y, or Z. So 26 letters, we can't use those 4. I've got 22 to choose from, and it doesn't say, yeah, it must be different letters, 2 different letters. So we can't use the same one. So we're down to 21 letters there. 4 different digits, 4 different digits. So I can use any digit to start. There are 10 digits. I've used 1, I can't repeat it, they must be different. I've used 2, I can't repeat it, and I've used 3 now, so I've got 7 choices left. If I expand that out, we get 2,328,480. All right, so that's using the fundamental counting principle. If you use the idea of permutations, we're going to look at our N and R. So I can't use 4 letters. So I've got 22 letters in the alphabet to choose from. I'm going to choose any 2. And then I've got 4 digits, 10 digits I can choose from. I need any 4. All right. If you do that on your calculator, you're going to get the exact same value. These things are equal. All right. In many cases involving simple permutations, the fundamental counting principle can also be used in place of the permutation formulas. They both work. As long as you show your work, you're going to be fine. You can choose whichever method you like. We will definitely be dealing with permutation notation again. All right, so questions 7 through 14. Let's give those a try.